Alright, welcome everyone to the live stream on graph theory. So the last time around, we looked at counting, we looked at the inclusion-exclusion principle, we looked at some what we call counting arguments, and now we can go ahead to sort of apply some of it into this area called graph theory. Now graph theory, of course, you can go into the theoretical aspect, but in terms of its applications, it's abundant. You can represent all sorts of data using graphs, and later on we'll look at another variant of a graph, a special type called a tree, and these objects are really useful to represent data. You will definitely see a lot of them if you ever take a module or a course on data structures and algorithms. That's definitely gonna be the case. So in fact, that might be the most useful aspect of discrete math to my understanding. All the proof techniques help you lead up to have a quick overview, a summary of graphs. And there are many different types of graphs and all that good stuff later on when you further your studies in this area. But as an introduction, having an introduction to graphs, an overview of graphs might be really helpful. So let's just very quickly talk about graphs. And over here, what are we talking about here? An undirected graph is an ordered pair of two things. So basically, let's represent it as a picture. Something like this. Something like that, right? So this is a graph. It is represented by the vertex set V. And in this case, these are the points. So this is 1, 2, 3, 4. Sometimes we call them vertices, we call them the nodes, we call them vertices, points, nodes. These are the common terminology to describe these ideas. And when it comes to an edge set, we have an edge set. We can represent these edges using graph theoretic notation, such as 1, 2, 1, 3, and 3. The idea here is that each pair of numbers encodes the side in which, the edge in which that connects these 2 points. So in this case, 1, 2 represents this edge that connects 1 and 2 together. 1, 3 represents the edge connecting 1 and 3 together. And 3 is the edge representing, 3 connects the edge to itself. So in a sense, although this is a really might be potentially confusing notation, what we actually mean over here is actually the set containing 1 and 2. This will encode the side that connects 1 and 2 together. The set containing 1 and 3. This will encode the side containing 1 and 3 together. And finally, the set containing 3, which encodes the loop. Right, so that's the idea there. So each element of the vertex set is called a vertex or a node or a point, and each item in the edge set is called an edge, right? It's called an edge, and it's of this form. When there's no ambiguity, we will denote it this way. However, as we've seen just now, if we denote 3, 3, or rather the set containing 3 as 3, it's a little bit ambiguous. So when it comes to loops, we try not to do this notation. This is just really confusing all around. Okay, now with that in mind, we can consider this situation here. We'll let Kn denote an undirected graph with n vertices and no loops, and suppose that there is an edge between any pair of distinct vertices. We're going to draw each of these guys, and a loop, as we've seen, is an edge of the form the point connecting to itself. So we don't want those kind of loops. So let's see how to draw them one by one. Let's start with K1. K1 is an undirected graph with one vertex and no loops. So it's one vertex, no loops. And so we're getting one vertex. There's no loops, so we can't really have any other edges. That's it for K1. That's literally it. Right? So let me write it this way. Let's do it this way because I want to sort of highlight a point later on. This will let n denote a bunch of numbers that we want to draw, and Kn will denote the complete graph with that number of vertices. We definitely will need more space, so that will probably be important there. Okay, so that will be the complete graph of one vertex on one vertex. What about a complete graph on two vertices? Well, we have two vertices, so let's draw the two vertices, and we need to connect them by an edge. Like this. We need to connect them by an edge. And, well, we can... Any other edge can we include? Well, we can't do a duplicate edge. It's actually the same edge as this guy. Loops. There are no loops, so we're done. What about 3 edges? Let's take a look. We get 3 points. And now we need to connect them using 3 edges. And then any other loops? Well, we can't really loop, and we can't really go further than that. Now, perhaps we can draw this in a slightly more systematic way, because it's been rather haphazard and it might not be so easy to generalize. So let's start from the 2 vertices case. We can just redraw the 2 vertices case. And now the third vertex basically asks us to take this guy and connect it to everyone else. Right? We want to connect this guy to everyone else. So these are the new edges that we can add into the diagram. Now, this might be a really useful way to think about it, because when we go to 4 and 5, this will be a systematic way to extend the pattern, in a sense. So here are 4 vertices. Let's draw in the initial 3 edges from the previous guy. And now we need to connect this vertex with every other vertex. So we take this guy, we'll connect it to here, here, and here. We want to take this guy and connect it to everyone it knows, it can possibly know. This might be an interesting strategy, because you can now generalize this to the complete graph with 5 vertices. And here's how we might go about it. So here are 5 vertices. Let's write it in a pentagon. Let's draw the complete graph of 4 vertices. And some of you might see where I'm going with this. And there's a really useful technique in graph theory, which my friend calls it the graph theory hack. If you have no idea how to prove anything, you can always rely on this one useful hack. It's gonna be helpful. Now, for 5, you have this guy over here. So this is the 5th vertex. You can build it up, the complete graph of 5 vertices with 5 vertices. You can build that up using the complete graph with 4 vertices. So how do we do it? We'll take this guy and connect it to everyone else. And that's literally it. So if we connect it to everyone else, you get the complete graph on 5 vertices. Now, that is actually a really, really interesting insight, because now we can actually ask a question, and then we're probably going to need to repeat this diagram over here. So here is the question. Based on how we drew the complete graphs, how can we calculate the size of a complete graph, or rather the number of edges of the complete graph? Now, we have actually developed a very interesting pattern here. And there are a few ways to develop this, but here's a really, really interesting pattern. We'll look at some other ways to do the counting as well. But here's the interesting pattern over here. The first one has no edge. The second one has the previous situation of no edges plus 1 edge, because there's currently 1 point in the graph and we need to connect this point to every single other point. And therefore, for this point, there is a total of 1 extra edge we need to connect. Now, for the 3 vertex situation, we started out with 1 edge, right? We started out with 1 edge. In fact, it comes from the complete graph on 2 vertices, the 2 vertex situation. And now we need to take this guy and connect this point to each of the 2 vertices. And what that means is that, well, we need to add 2 edges. Now, what about the 4 vertex situation? You take a vertex and you connect it to the 3 existing vertices. So that's 0 plus 1 plus 2 plus 3. And for the n equals to 5 situation, the 5 vertex situation, you take the 4 vertex situation and you add 4 edges to it. You add 4 edges to it. And I think the pattern is starting to emerge. As you can see, it actually is what we call the triangular numbers, the arithmetic progression, whatever you want to call it. The number of edges in Kn is going to be, and you can prove this using induction. And this is what I mean by the graph theory trick. Let me elaborate on that. Now, so by induction, and you can check this out for yourself, I'm going to denote exercises in green as green stars. When I put a green star there, you can check it via an exercise. You can prove by induction that the number of edges has to be 0 plus 1 plus 2 all the way to n minus 2 and minus 1. And this tells us that the total number is going to be the total number of terms, right? So maybe let's write that again. The total number of terms times the first term plus the last term, which gives us this expression here. You can prove it by induction and you can go ahead and solve it. So this is what I mean by the hack. Whenever you want to solve a graph theory problem, most of the time, the easiest way to solve it is using induction. Any result that you ever need to prove, you probably can prove it using induction, at least when we deal with finite graphs. In this case, finite graphs are when you have a total number, you have a finite number of vertices. Right, so this is where induction is really, really powerful. You can use this result. You can use this technique to do pretty much any kind of graph theory problem. This one, in this case, we were looking at the number of vertices, once again, just like before. So that's a really, really powerful technique. Feel free to use it as and when you wish. Now, sometimes it might be just easier to count it directly, and we're going to look at some questions where that is the situation. So here's the question. Find the number of undirected graphs where we have 3 vertices. So in this case, suppose we have 3 vertices like this, 1, 2, and 3. And we want to find the number of undirected graphs. In fact, let's be more precise here. We'll let the vertex set be A, B, C. And more precisely, we want to find the number of ways, number of graphs G with these vertices. So maybe this is a little bit ambiguous, I'll have to admit. I think what I mean is V of G is A, B, and C. I think this is a little bit more clear of a question. Alright, this is a bit clearer. So given that we have a fixed vertex set, how many graphs can we find? That is the question. So that is our question, and we can maybe just start ahead. We can start thinking about what we mean by graphs with this. Well, let's just draw a picture. In fact, sometimes we ditch the points altogether. We just put A, B, and C, right? And we can ask, what are the possible edges that we could connect? We may not want to connect them, may or may not want to connect them, but we could connect them. And these are the ones we could connect A and B together. We could connect A and C together. We could connect B and C together. And we could connect each of these terms together as well. Each of these edges could either be chosen or not chosen. Right? So in other words, since we have a total of 1, 2, 3, 4, 5, and 6 of these edges, including loops, the total number of graphs is equal to the total number of possible choices. Each edge can have 2 choices, so it will be 2 to the power of 6, right? Because each edge has 2 choices. You can justify this by saying each of the 6 edges has 2 choices. either included or excluded in the graph. So that's how we can maybe get a little bit more clearly justify how we got the 2 to the 6. That's where we come from, because we have 6 different possible edges, and then we can we may or may not want to include or exclude them, right? So there's that. Now I believe we are going to need this information for the next part. So come back here. Okay, so once again, VG over here really means V of G equals to A, B, and C. Just these 3 vertices. And we want to find the number of undirected graphs with no loops. So what can we do here? We have a total number of graphs, but how many graphs do we have with no loops? Well, no loops means that we have to exclude each of these guys. We have to exclude them because we do not want any loops. And so we can only freely choose, right? For these particular edges, there's only one choice. Don't include them. Totally do not include them at all. But for these guys, we still have free choice. We can still either include or exclude these edges. Therefore, the total number of graphs with no loops is 2 to the 3, which is equal to 8. You can also still justify it, right? And I leave it for you to justify it using some English, right? Just justify using some English. So the idea is there, right? Because we want to exclude the loops. And we have choices. We have 2 choices each for each of the non-looped edges. So there's that. We're probably going to need this information later on. I believe we do. So here's the next question. Once again, VG here refers to the set containing A, B, and C. Find the number of undirected graphs G with VG equals to ABC, and that we have a cycle. Now what that means is that we now insist on having a cycle. And what exactly is a cycle? A cycle is basically, as the name suggests, a cycle, right? You sort of start at one point, you end up at the same point, but you visit other guys. So a loop doesn't visit anyone else, you end up at your own base right away. A cycle means you cycle through other things before coming back. And because A to B is actually the same edge as B to A, you cannot have cycles of length 2. You can have directed cycles with length 2. That's if we studied directed graphs, which we're not doing this time around. But you can have all your cycles will be of at least length 3. Because if it has length 1, you end up with a vanilla loop. And if you have length 2, it's not possible. So your cycles must have minimum length bigger than or equal to 3. So we need to include a cycle. So we need to include these guys. These guys must be included. And in terms of the loops, we have free choice. We can actually choose whether to include the loops or not. So the total number of a cycle, at least one cycle, we have a total of 3 loops. We can either choose to include them or not. So there will be 2 to the 3, which is 8 once again. Just want to emphasize that in the no loops situation, this 3 and this 3 represent completely different situations. The 3 in the no loop situation tells us that we can freely choose to connect them or not. The 3 in the second situation tells us about the loops. So that's a slightly different, slightly confusing thing about counting, is that you have the same number but it can represent some different object. So that's the art aspect of the idea. This is the technical definition that describes a cycle. You have a starting point and then you can end off, well, you start off with x1, you go to x2, you go to x3, and so on and so forth, all the way to xl. That'd be the xl over here. And then you go back to the base. So you get a cycle. See? You have a cycle. That's the intuitive picture of a cycle there. And finally, here's the question. We want to find the number of undirected graphs with vertex set A, B, and C that are cyclic. So, what does it mean that a graph is cyclic? A cyclic graph is one with at least one loop or at least one cycle. So that's the idea. Cyclic means you have at least one loop or you have at least one cycle, and you are acyclic if you are not cyclic. That's it, right? So you can define this way. G is acyclic precisely when G is not cyclic. That's our definition of a graph being cyclic or not. What does that mean? We'll need the number of cyclic graphs. And what that means is that we need the number of graphs with either at least one loop or, and I'm going to use the union here because we're going to apply some results from the past, and or at least one cycle. And now, what can we do here? Well, this is we're counting a union, right? We're counting a union. Whenever we want to count a union, if we only need an estimate, we can use what we've discussed previously called the union bound, which says that the number of items in both is upper bounded by the sum of the items. But if we want an exact number, we can use the inclusion-exclusion principle, which helps us tighten this result into an equality. It will be A plus B minus the intersection. And in this situation, we want to count the exact number. So let's go ahead to use the inclusion-exclusion principle over here. And this will be the number of graphs with at least one loop plus the number of graphs with at least one cycle minus the number of graphs with at least one loop and at least one cycle. So that's how we can use the inclusion-exclusion principle. And this allows us to reduce the counting problem to just three other items. These three items here, right? So we're going to use the inclusion-exclusion principle right about here. We can use this principle over here. And this allows us to calculate each of these items separately. Now, how do we count the number of items with at least one loop? That will be the total number of graphs minus the graphs with no loops, right? Because if you want at least one loop, that is the complement of no loops. So this is going to simplify to 64 minus 8. What about the number of graphs with at least one cycle? Well, the number of graphs with at least one cycle is given to us as the number 8. So we can just plot that in right there. And what remains is for us to calculate the number of graphs with at least one loop and at least one cycle. And what does that mean? It means, actually, we could sort of decompose this to mean at least one cycle and no loops, right? So more strictly speaking, this number here could be reinterpreted to mean the number of cycles, the number of graphs with at least one cycle and no loop. So let's just maybe erase that. We could actually condense all of this to mean the number of graphs with at least one cycle and no loop. Which means that we insist on choosing these guys and we insist on not choosing these guys. Which gives us actually just one cycle. So we just have one cycle right there. And our final answer is going to be 57. 57? Is it 57? I think it's 57. I think it's 57. Yeah, let me do a quick verification of the solution. I think this is correct, but I need to verify just in a moment. There we go, 57. So we're good to go. Alright, what is up for us next? Okay, I think we're gonna do some fun stuff in just a moment. That we want to sort of make sense of some ideas in graph theory, and there are some interesting ideas here for us. So this is going to be pretty interesting. Now, firstly, we have this thing called a path extension lemma. So, well, firstly, what's a path? And secondly, what do you mean by extending the path? And thirdly, why on earth are we bothering with this claim? Well, this claim is going to be useful because, roughly speaking, it's going to tell us about how you can sort of extend paths. I mean, the name itself suggests that you can extend paths. Now, what exactly is a path? So let U and V be 2 points in a graph, and let's just say it has these other points here for the sake of discussion. Right, a path basically means that you have some edges that go from U to V. That's what a path is, right? You have a bunch of edges inside the graph that helps you get from U to V, like this. That's the idea, and we insist that the path does not self-intersect. So we do not consider, say instead we go this way, like this, right? So then some people will say this whole thing is a path. We do not consider that because we want to consider the length of a path. If we do this, then we could just loop as much as we want and then go back out. So for a path, we are not going to define it with self-intersections. And so what is the path extension lemma for us? It basically says this. All right, so here's the idea of a path. Here's a quick idea. Here's the idea. If U and V, if you can find some path P that goes from U to V, and from V to W, you can find some other path Q, then you can find a path from U to W. I think that's pretty straightforward. There's a path P, there's a path Q between V and W in G. Then there's a path between U and W in G. I think from the diagram, it's pretty straightforward to establish the claim. But I want to sort of establish the proof here just to sort of highlight some techniques which we will use in order to bootstrap the argument. So we're gonna first make some, we'll first work with the special case. Now, we've drawn these two paths such that they do not intersect, right? So let's first start with that assumption. Now, could it be possible that U, V, and W are drawn this way? Say like this. The path from U to V looks a bit like this, and the path from V to W looks a bit like this. And then for some reason, for some weird reason, they decided to intersect over here. Could this be possible? Well, the answer is yes. That will bootstrap that situation in just a moment. But for now, let's prove it. Let's first suppose we'll let P denote a path between U and V, and Q denote the path between V and W. What do we have here? What do we have here? Well, the idea is, well, let's first work with the special case. Suppose P and Q do not intersect only at one point V. Intersect only at V. Now we do know they must intersect at least at V, right? Because P goes to V and Q goes to, well, Q goes from V to W. So since P and Q intersect only at V, we can very quickly check that then none of Then the vertices in P, we can write it this way, the vertices in P and the intersecting the vertices at Q will only be V. Now what that means is that the edges of P, and you can very quickly check this result, we'll leave it as an exercise. The edges of P and the edges of Q do not intersect. So we can now define the path, say R, to be the collection of vertices from in P and in Q, and the edges in P and in Q. We put them all together. Define R to be in this manner. Then R has to be a path between U and V. Well, U and W. More precisely, U and W. So what's going on here? Why do we get a path here? Let's very quickly verify this claim, right? So we can go from, essentially the idea is this, right? The reason why is that, okay, we have VP is equal to U, and then say the vertices inside P, and then the vertices inside Q. Right, the vertices inside P and the vertices inside of Q. And then we have the edges in P, which is say UP1, UP2, well, P1, P2, all the way to PLV and VQ1, and they don't intersect, right? Because they don't intersect, as we've seen over here. VQ1 all the way to QMW. This thing, by definition, satisfies the definition of a path, right? So this thing, right, tells us that R is a path. We are sort of verifying the definition of a path. We verify the definition of a path. So this is the special case in which they intersect only at V. But what about the situation when they do intersect? And we're a bit sort of, how do we go about this? So here's the technique, and you will see this technique quite a bit in some of the various proofs. I wouldn't prove all of it, but we've already proven the situation when they intersect. So let's clear that up. So we've already proved this situation. Now suppose, on the other hand, P and Q intersect at some other point, at more than 2 points. So V is 1 point and then you have another point. That tells us that there has to be some xi inside the vertices of P such that xi lies inside both P and Q. No, that's what it means. And so, why is this useful for us? Then we can define, say, I star to be the smallest of the integers, such that xi lies inside V of P intersect V of Q. So the idea is this: the paths could intersect in many different ways, right? Especially when we're dealing with discrete objects. So the path may look like this. It could look like this, right? It intersects a bunch of times. We'll let I star be the first one. That's what it means to be the minimum, means among all of the different indices where you get the intersections. I star is going to be the first one. Right? I star is going to be the first one. What does that mean? if I star is going to be the first one, then everything else before it is not going to connect with, is not going to intersect the path. So in fact, we can now check, and I'm going to let you guys check this, that if we define R, right, check that we'll define P star to be the path between U and xi. So in other words, we just only want to contain, we only want to talk about this path over here. Right. P star will be the path between U and xi. Check that this P star, you can define this, if we have this path and we have this next path between xi and w. Check that these two things are well defined. You can check this out. Check that it does meet the definition of the path, no intersections, all that good stuff. And then we can use this to let me take a moment here. Let me just take a look. Between xi and w. Yeah, this should be well defined. So check that it's well defined. Then, by the first case, then we'll define R star to be the connection from, well, we don't have to define R star. What this means is that we can find a path from U to xi star. This will be xi star, give me a moment. And then a path from xi star to w, but now this satisfies this situation that they only intersect. We can check, okay, then P star and Q star intersect only at xi star. Again, you can check this claim. And these, by A, tell us that there is a path from U to W. So sort of like you start with a special case when you don't get any intersections, and then you slowly generalize it into the part when they do intersect, you reduce that into the non-intersecting situation. So really a lot of ideas in graph theory is sort of, we start with a special case and then we sort of build up, use that special case to build up the general situation, either by induction or some other kind of argument like what we did here in the path extension lemma. So that is the idea over there. It's a really, really interesting idea, and feel free to use this idea when incorporate this idea into your proofs. We have another lemma over here. This is called the two-path lemma, or at least I call it the two-path lemma. Depending on your module, you will have specific theorem code numbers for this. I think you can just use it freely, but make sure you've proved it in your module. So here's the one. Let G be an undirected graph with no loop. So we'll let G be an undirected graph with no loop. We'll say that G is cyclic if and only if it has two vertices U and V, between which there are two distinct paths. So it's if and only if, right? So we need to go ahead to prove in two directions. The first direction is, suppose G, which we will denote by V of G, E of G, is cyclic. Here's the idea, here's a picture. Now if it's cyclic, if it does not have any loop, it must have a cycle, right? So you must have something that looks like this. You must have something that at least minimally looks like a triangle. It could be longer. It could be longer. Nobody knows. Nobody cares, really. So we have a cycle, and in this situation, again, all the edges in the cycle don't intersect, right? So we insist that the edges in the cycle don't intersect. Otherwise, you could just, keep going forever and then come back. So which is not the most useful notion for our purposes. So suppose G is cyclic, then, well, not then, but since G has no loop, we're taking our cues here, G has no loop, it has a cycle that looks like U to W to V. And I'm gonna illustrate this in the following way. You can travel around the world however you want to W. You may have lots of edges there, you may have just the edge from U to W, no one really cares. And then you can travel all the way again to V, and then you will connect U and V together. Then you can check that the first path defined by UV and the second path defined by U all the way to W all the way to V. The cycle ends up at U, so we need to end up at U over there because a cycle looks like this and it goes back to the original guy. You can check that these two things are paths. These guys are paths. Please feel free to check that. And since they are paths, therefore, there are two paths between U and V, right? And that's that. So if you have two paths between U and V, you're good to go. And that's basically the idea there. On the other hand, if you have two paths from U to V, we're going to have a situation that looks a bit like this. Here's our first path. Here's our second path. Again, this is a very nice situation in which there's no repeating intersections. But you could very well have a situation where the paths do indeed intersect. You could have this situation. So how do we resolve it? We'll use the exact same trick that we did just now. So firstly, we'll suppose that there are two vertices inside the graph such that there are two paths. We'll call this P1, P2 between U and V. So we'll call this P1 and P2. We'll call this P1. We'll call this P2. And we have these paths. Again, we'll suppose a special case. Special case A, P1 and P2 have intersect. In fact, we're going to do it this way. P1, the vertices of P1 and the vertices of P2 only intersect at U and V. So that's the first idea there. You only can intersect in these areas. So in other words, any other points inside, they can't intersect. So that's the first situation. And how do we present the case? So we'll let P1 will be U all the way to, we'll call this W1 all the way to V. Looks a bit like this. And P2 will look a bit like V all the way to W2 all the way to U. Then we can check that if we were to just combine them together, you get a cycle. And the idea is that in a cycle, we cannot have any intersections. We cannot have any self-intersections. We just need to check that there are no self-intersections. Maybe we can do it this way. Has no self-intersections, which tells us that this expression, we'll call this C. Is a cycle. And once C is a cycle, then we know that G is cyclic. So that is the special case in which we don't get any self-intersections. You might be wondering what happens if we do get self-intersections, and you will realize that the strategy is literally the same as what we did previously. So let's do that. Part B. So part B, suppose VP1 intersect VP2 equals to UV and some xi's. We don't know which xi's, but you know, some xi's. So in other words, it is, more precisely, it is a strictly bigger subset than U and V. Now it's to intersect somewhere. They have to intersect somewhere. We'll call this, again, we'll call this, say, xi star. And you might be wondering where we're going with the xi star business. We're going to use the exact same trick. We'll define I star to be the smallest index such that the path in P1, intersects the path in P2. We'll define it this way. And what does that tell us? That tells us that you can now check, again, that P1 that goes all the way to xi star and P2 that goes from xi star all the way to U intersect only at U and xi star. So you can check that the cycle has no self-intersections in the first case, and in the second case you can check that the new paths we created intersect only at this aspect, at these 2 points. And again, by defining the minimum this way, we sort of eliminate any other possibility. Sort of the minimum helps us really go down to the bare bones situation of, okay, fine, there are a bunch of intersections, fair enough, here's the minimum and no further, right? Anything less, then the guy's gotta intersect right away. So that's the trick, and I think the technical justification is using what we call the well-ordering principle. We can justify this trick by using the well-ordering principle. This minimum exists by the well-ordering principle, right? Because you have some integers that are you have a non-empty collection of integers such that this happens. So yeah, it exists by the well-ordering principle, and you can define it this way, so then now you can get just a cycle that looks like this. And yes, for this part of the live stream and this point in time, I will ask you guys to get some to resolve some of the statements on your own, because if I were to have to digress into elaborating them, this will be a really long live stream, and it's also not the most insightful as well. So you do want to verify some of these statements for yourself. So we call this the two-path lemma, because the idea is that if you can find two paths from between 2 points, like this, then you get a cycle, and vice versa. We can call this, we can generalize this idea, or not generalize, but we can sort of phrase a path, well, this is a cycle, pardon me, a path and a cycle as subgraphs. So it's like smaller graphs, because, well, all the points lie inside the original graph, as well as all of the vertices as well. And we get a proper subgraph when the two graphs are actually not equal to one another. So it's really smaller, actually smaller graph inside of G. Alright, so you can check that paths and cycles are subgraphs as well. Again, left an exercise, because you guys can do it. So here's a question, and this is a slightly more annoying question. I remember I was really annoyed when I solved this question, when I went ahead to try to solve it. So which of these graphs are isomorphic? Which of these are not isomorphic? And you need to justify your answer. So how do we go about it? Well, an isomorphism from one graph G1 to another graph G2 is a relabeling. Alright, so here's a technical definition. It's a bijection such that this holds. Basically, can you relabel one graph to get another? I'm going to use this as an illustration. So let's take this guy, and what we're going to do is we're going to flatten this. We're going to sort of flatten this into the background, something like this. Right? So the idea is almost like that. here's your cube. Or maybe we'll do it this way. Here's the cube that looks a bit like this. Right, looks a bit like this. And what we're gonna do is we're gonna redraw this cube to look a bit like this. We're sort of gonna flatten the top down onto the bottom. Like that. And so when we do this flattening, this cube-like structure is going to look a little bit like this. Well, if we call this the edges and then these are the sort of like the sides, what we have here is that we get 1, 2, 6, and 7. Like that. We're going to get the 8, 3, 5, 4 on the inside. And then we're gonna include the 1 and the 8s together. So as you can see, by converting it like this, we're getting something that looks a bit like this. Now, this graph and this graph, strictly speaking, are different because they have technically different connections. One is connected to 2 here, one is connected to here, but one is connected to 5 here, and here one is connected to 8. So they are different graphs. However, if we did a bit of relabeling, so how do we do a relabeling? Here's the idea. If we relabel it in this manner, so 1, 2, instead of 7, let's suppose we have a 3, and let's perhaps put our relabeling in a table over here. So here's the initial number and here's our relabeling. If we start off with 1 and we want to obtain this shape, so we're going to get a bit like this. If we do a bit of relabeling, 1 gets relabeled to itself, or well, 1 gets relabeled to itself, so that's not a problem there. 2 will get relabeled again to itself, so there's not a problem there. But here's the more interesting part. 3 over here gets relabeled to 6. So 3 will switch over to 6. 4 over here will get relabeled to 7. So we can write 4, 7 like that. And you can check that 5 will go to 8, 6 will go to 4, 7 goes to 3, and 8 goes to 5. Right? And this will actually give us what we call a composition of cyclic permutations. That's not important. But with this relabeling, we get from this original graph, so this essentially is what we call redrawing. And then we can get this graph by redrawing. Well, it's actually the same graph. These two things are the same graph. So we redraw the graph and then we relabel it. If we can do such relabeling, we can say that these two graphs, 1 and 3, right, we can conclude from this relabeling that 1 and 3 are isomorphic. And I am skipping a bunch of details here, checking about some symmetric relations and whatnot. But you can go and check it out as well. Okay, so in other words, we know that these two guys must be isomorphic to one another. Now, we would suspect that 2 and 4 are isomorphic as well, although it might take a bit of effort to establish that claim. So we're gonna keep 3 in the mix here because we have something important to talk about in just a moment. But we know that 1 is out of the picture, so we know that 1 and 3 are isomorphic, so we can put 3 aside. We'll come back to 3 in just a moment. Now, for 2 and 4, I struggled a few times with obtaining an isomorphism. But I think I should try it again. I should try to create an isomorphism that works. And so, what I might try to do might look a little bit like this. Okay, here's how we're gonna do it. We're gonna start with the number 1. We're gonna connect 1 to 8 like this. We're gonna connect it to 2 like this. And then we're gonna yeet over and connect 6 like this. So there'll be 1 and 6. Okay, so I'm just gonna risk it here. I hope this works. We're gonna connect 2 and 3 together like this. We're gonna connect 2 and 3 together like this, so that will get rid of this edge. And I'm gonna not just go to 4 right away, but we're going to, we know 2 connects to 1 and 3. We're gonna connect 2 to 4, but I'm gonna yeet the 4 over here. And I don't think this is a good idea. This is not a good idea. Because eventually I know that the 6 and 4s are not gonna connect. So this is not the right approach. This is not a good approach. Let's try that again. Now there are a few approaches to solving this, but I want to try this rather straightforward approach. Now we could try a approach where we can try the flattening approach once again. We could try the flattening approach like this. 1, 2, 6, 7, 8, 3, 5, and 4. And we could attach them like this. Well, this is a bit confusing. We could sort of attach them like this. Right, 6 and 7, 6 and 5. So we could attach them this way, and part of me is thinking the crossovers look really, really sus. And so I'm thinking to myself, okay, is there a way sort of to obtain these crossovers with relative ease? It is messing with my brain here. Okay, let's try this out. Let's just try this out. Okay, let's just try 1, and then we're gonna go with 2. Okay, we're gonna go with 2 here. We're gonna go with not 6 on the other side, but we're gonna put 6 over here. Okay, we're gonna put 6 over here. Let's try instead we threw the 8 the other side. So just now what happened, what failed earlier on is that we put the 6 and the 8s in the wrong positions. So now we're trying to sort of do that. And I'm just gonna see whether this works. So let's try this out. And then 2, we're gonna put the 3 beside the 2. Like this. And we're gonna yeet the 4 over to the other side. I think this time it's gonna work. Alright, so now 3, we can connect the 3 to 5 and 7, and 5 I'm going to put it here, and 7 I'm going to put it here. I think this is going to work. Oops. I think this is going to work. Like that. Now 5, well 5 here is going to be connected to 8 and 6. I think this works, yeah. And then 8 is connected to 5 and 4 and 1. There we go. 4 is connected to 2, 7 and 6. 2, 7 and 8. There we go. And 7 is connected to 6. So that is how we do our relabeling. We can relabel, and I will let you guys do the relabeling. Well, not really relabeling. No, this is not relabeling. The relabeling happens over here. Apologies. The relabeling happens here. These are all just redrawing the same shape. So more precisely, these are both redrawing. And then you can finally relabel it. And I'll leave you guys to check for the isomorphism. This tells us that 2 and 4 indeed are isomorphic. 2 and 4 indeed are isomorphic. That's a little bit trickier. Obviously, it takes a little bit more effort to draw the graph, and unfortunately, we don't really have any fixed algorithm by which we can do this. I wish we could, but unfortunately, it's not as readily available to us as we hoped. So that is not very convenient, but that's alright, we'll get there. So for that purpose, I'm gonna copy and, oh, darn it. I'm gonna once again delete 2 because we know it's isomorphic to 4. And now ask the question, between these two graphs, are they isomorphic? Now we're tempted to say no, and we're tempted to say that it's no because of these, because of these crisscrossy thingies over here. But that's not a good argument, right? It could easily crisscross. Again, this graph, well, give me a moment. This graph here is isomorphic to this graph because we can basically redraw this guy to get 1, 2, 3, 4. Right? And these two things are isomorphic. So just because they crisscross does not mean they are not isomorphic. Okay? So this is not a good argument. There are a few ways to argue the case, but here's a really clean observation. Now you could prove this a bit more rigorously, but we probably don't need to. If we look carefully, every cycle in part 3 has even length. For example, like this. This is a cycle with 4 edges, length 4. What about this strip? That's 6. Right, that's 6 edges. What about this strip? Wow, it's a really long strip, but that's actually just 8 edges. What about this strip? It's actually isomorphic to the previous strip. So any strip that you ever wanted will have even length, right? You either have, every cycle you have will have even length, but the cycle 1, 2, 3, 4, 5, 1 in 4 has length 5, which is odd. For example, 1, 2, 3, 4, 1, 2, 3, 4, 5. And come back. 1, 2, 3, 4, 5 edges. So we have 5 edges, and this is a fundamentally different feature between the two graphs. What does it mean for two graphs to be isomorphic? It means essentially they are the same with different labeling. But in this situation, because we have a fundamentally different feature in a sense between the two graphs, there is no amount of relabeling that will help this guy have a cycle with odd length. It is not possible, and therefore we can conclude that 3 and 4 are not isomorphic. Here's the idea, because every cycle in 3 you have an even length, and you have a length in, you have a cycle in the other, you have a cycle in the other graph with odd length, right? So just by looking at the graphs, you can tell whether they are isomorphic or not, although it's actually not as easy to look at them, right? It's even harder when we need to deal with large amounts of information. So that is a slightly challenging aspect of graph theory. Please let us know if you have a general formula for proving that two graphs are isomorphic. You'll be famous in the world. Alright, here's another question. For n equals to 2, 3, and 4, count the number of undirected graphs with n vertices and no loops. We'll treat isomorphic graphs as 1. So let's suppose we have n equals to 2. How many undirected graphs do we have? Well, let's start with 2 vertices. And, well, this is one graph where they have no edge. In fact, we have, we want to sort of harken back to the previous result, right? So let's just sort of go back to the previous result. We call it in some sense the biggest graph of n vertices. That will be the complete graph. And we've seen the formula is actually n times n minus 1 over 2. So here, if we consider the largest possible graph, is going to have this number of edges, which is 1. So in other words, for the n equals to 2 case, we have a bunch of possibilities, right? In fact, we're going to draw it this way. For n equals to 2, we can either have 0 edges, or 1 edge graphs. And that will look a bit like this. 0 edges and 1 edge. And we have no loops, so this way of counting actually works. So that is basically a relatively systematic way to check it. It might take a bit of effort, but we'll see that in just a moment. So how about for the 3 graph situation? Well, once again, the number of edges for the biggest situation, in a sense, like the biggest set situation, it will be this number, which is 3 edges. That's as large as you can go. So let's check to see that we get the 3 edges. So the first thing is we have a 0 edge situation. We start with 0 edges. Now we can ask about, what about the 1 edge situation? We could add the edge in any one of these 3 aspects. However, because it's isomorphic, if you add it to this guy, right? So if you get this shape, and you get this shape, or you get this shape, these 3 graphs are actually all isomorphic to one another. You can rotate them, you can relabel them, you're going to get something that's isomorphic. And that means you get the most basic shape over here. I think you can extend it like this, or you can extend it like this, but I think it does take a little bit of effort to do that. I rather extend it in this way, because it's a bit more systematic that way. What about for the 2 edge situation? You can start from the base situation, and you will be left with either, well, you have 2 options. You can either add the edge over here, or you can add the edge over here. You can add the edge in either of these choices. But once again, shape-wise, they're actually the same shape. So actually they're isomorphic. And so you actually have just 1 graph. Finally, for 3 edges, you can add the last edge, and you're good to go. So 3 edges, or rather 3 vertices are really clean. The messy part comes with 4 vertices. Okay, so let's first establish how many possibilities there probably will be. We have a total of 4 times 4 minus 1 over 2. That's 6 edges. So we need to consider graphs with these number of edges. Let's start again with 4 vertices. Nothing, right? Nothing. No edges. What about 1 edge? Again, just 1 edge. And actually, if you were to add the edge here instead, like this, oops. If you added the edge like this instead, it's going to be, once again, isomorphic to the base situation. So you're not missing out much. Now the fun stuff happens in the next part over here when it comes to 2 edges. So we could start with the base situation and then add our edges essentially in 5 different ways. We could add the edges in one of these ways. So what I mean, we can add the edge either oops, I think I added too many. Whoops. There we go, 5. We either add the edge here, or we could 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 add the edge here. We have many options. But here's the fun bit. You'll notice that this option, this option, this option, this option essentially has the same shape of this guy. So these 4 are actually all isomorphic to one another. And so we can ignore the extras. We can totally ignore the extras. It's totally fine. And likewise, you can check this out for the 3-case situation as well. In fact, we're going to do the 3-case situation, and I'll let you check the 3 edges situation, and I'll let you check the 4 edges situation and the 5 edges situation on your own. So, for the 3 edges situation, looks a bit like this. Well, we can start off with the 3 edges over here, and then we can try to add up, we can try to include all of the different possible new edges. So let's start with this shape, 4 of them. We will add a new shape, we'll add a new edge. Oops. We can add any of these new edges. 1, 2, 3, and 4. We can add any of these edges. And it turns out that these two here are going to be isomorphic. Right? So actually, this last one here is pretty redundant. And you might be wondering to yourself, wait a minute, what about the other situation? What about the other parts? Well, we can start with this shape, and we can add our third edge in 4 different ways. The first way is here, second way, third way, and fourth way. But you notice, firstly, these guys are all basically graphs of this form. They're essentially straight lines. Yeah. And furthermore, they're all isomorphic to this guy. And this guy, furthermore, is isomorphic to this guy, because it's all essentially a straight line. They're all essentially straight lines. So in fact, you do not get any more graphs. You end up with a total of 3 over here. So you have 2 here, you have 1 here, you have 1 here. And you can repeat the process for 4, 5, and 6. Now I'm gonna let you guys go ahead to do that, and you might actually observe some interesting patterns. Do let me know if you see any interesting patterns in the comment section below. And that's the n equals to, that's the 4 edges situation. What about the 5 edges situation? We're gonna get this. And the 6 edges situation is basically our complete graph. Now you might notice a few interesting patterns over here. So do let me know in the comment section below if these patterns caught your eye. We probably will look at some of these ideas. We'll look at the idea that is responsible for this pattern in just a moment. Okay. Now another idea in graphs is a really useful idea called connectedness. It's very useful to talk about things that are connected to one another. Essentially, you can travel from one point to another, right? So we say that the graph is connected if you can always find a path from this to this, alright? So maybe, for example, it looks a bit like this. Maybe it has a cycle somehow, right? But essentially, any point here between any 2 points, you can always find a path. That's always possible, right? So say this and this, you can find this path. Say this, say this and this. Say this and this, you can find a path. And in our situation, you can actually find 2 paths. So that's what we might connected. And we call this a connected component, roughly speaking, if it's the largest connected subgraph. In a sense, it's some form of largeness of a subgraph. So here's the idea. If you have any other subgraph and you know that it's connected, and furthermore, you know that H is, a subgraph of K, in order to capture the idea of H being the biggest, if H is smaller than K, then there's only one possibility. H must be equal to K. Okay, so that's the claim. Alright, that's the definition. And here's our claim. Suppose you have a vertex V, then you can always find a unique connected component HV that contains V. Alright, so here's the idea of the proof. Here's the idea. So roughly speaking, if your graph looks like this, if it is V, it will be connected to some other things, right? And then perhaps nothing more. You can always find firstly a connected component, and secondly, this connected component is unique. There's only one. And it does make sense, right? That sort of highlights the idea of a maximal kind of object. But let's just see how we can prove this in a bit more detail. So let's first define HV to be this particular subgraph, right? So let's define HV by the following definitions. We define its vertices to be any item that has a path to V, right? There's a path to V. So any item, any vertex, such that there is a path in G between V and X. Oops. Well, no, it was awkward and embarrassing. Try that again. And we'll define E of HV to be precisely all of the different possible connections. So it will be the XYs in EG with the property that XY is actually, well, X and Y are in the vertices of the original connected component. Well, we just need to check that HV is connected. Alright, so here's the idea. How do we check that HV is connected? Well, firstly, we need to check it's connected. Secondly, we need to check is the connected component. So we have a bit of work to do in order to establish this claim. So firstly, it is connected. How do we check that it is connected? We need to show that for any two vertices, we can find a path. So let's fix, say, R and S inside the vertex set. This tells us that there exists a path between R and V in G, right? We can find a path between R and V in G, and this means that there exists a path between R and S in, well, V and S in G. And finally, we can combine this information using our path extension. We can find a path between R and S in G. Does this tell us that HV is connected? No, it just tells us that you have a path in G. Now there's a little bit of subtlety there. Isn't the path in G a path in HV? Well, what if you have this path? This path is in G but not in HV. So just because you have a path in G does not necessarily mean it's in HV. But if we can show that we have a path in between, that we can find a path inside HV, if we can show that the path between RV and G actually is a path in HV, then we still get our conclusion as per normal. So that's the idea. How do we know that a path, here's a question. How do you know a path in G will give us a path in HV? How do we know that? We don't actually know that for sure. We actually need to check, and we actually need to establish this claim properly. And so, with that claim, we will come back to this in just a moment. So this is our claim. This will be our lemma, I think. We'll call this a lemma that we will prove in just a moment. Right? So what we have done here is shown that because if under this lemma is true, if this lemma is true, then we can get this conclusion. This tells us that HV is connected. But we need to check that it is a connected component. So let's go ahead to do that. So we have already shown that HV is connected. In fact, we probably need a definition, so let me erase everything. Right? We have already shown that HV is connected. But how do we know that it is a connected component? How do we show that HV is connected component? So here's how we do it. Claim HV is a connected component. We need to check that for any subgraph, if it is connected and it contains H, then it must be the one and the same. So here's a check, here's a proof. Okay, fix K, fix a subgraph K of G such that K is connected and H is a subgraph of K. Right, so suppose we have these guys over here. What does this tell us? This tells us that all the vertices in H lie inside K and all of the edges in H lie inside K. And well, this should be HV. Let me write that again. HV. Right, HV and all of that. So that is the question, right? That is the question. How do we check that we do in fact get equality? So here's the claim that V of K is a subset of V of HV and E of K is a subset of E of HV. Right, so that is the question, and here's the idea, right? So here's my idea. We'll need to fix a vertex in K and show that it belongs to HV. Alright, so how do we go about it? I think I have an idea. So we'll fix a vertex V inside V of K. Well, let's not fix V, we used V already, so let's use the letter U instead. We'll fix the point U. And since V is inside K as well, since V lies inside of K, because V of HV, let me be more precise here. Since V lies inside V of HV, which is a subset of V of K, there is a path between U and V in G, right? That's what it means for a K to be connected, such that, well, in K, more precisely, in K, such that there's a path between U and V in K, right? Since, because K is connected. However, this path between U and V in K, since K is a subgraph of G, you have a path between U and V in G. But if you have a path in between U and V in G, it meets this condition. It meets this condition, which tells us that U must lie inside the vertex set of HV. And therefore, we are done with this claim. Now, that's very surprising, because now, if you consider the edges in K, right, the edges in K, so we'll fix any edge in K, then we know that RS is an edge in K. We know that R and S both lie inside the vertex set of K, but this is the vertex set of HV. And therefore, this tells us that RS must lie inside the edge set of HV. Because if R and S are in VK, if R and S are in VHV, then their edge must lie by definition inside EHV. So we've shown that EK is a subset of EHV. In other words, this establishes that the vertex set of K lies inside HV, and this establishes that the edge set of K lies inside the edge set of HV. So that's the idea. Sort of our definition of HV is a really, really sneaky definition. It really encompasses every single possible edge you could possibly think that connects to V. That's the idea. And because of the way we defined it here, we are able to get these properties. Therefore, HV is a connected component. Right? HV must be a connected component because no matter which subgraph you have, if it's connected and HV is a subgraph of that, we have shown that the reverse inclusions to the original inclusions hold, which tells us that H equals to, well, H equals to K as required. H must equal to K. That's the only possibility. There's one more subtlety in this part here, and that is me assuming that it's unique. It's like, wait a minute, what's with unique? We'll come to uniqueness in just a moment. Actually, it's not too bad. It's actually not too bad to show uniqueness. So here's a quick check, or rather a quick claim that this connected component must be unique. So let's very quickly show the uniqueness. So we've already shown that. Let me clean up the board. We've already shown that HV is not just connected, but a connected component. It is a connected component. But is it the connected component? Is it unique? And I think the answer is yes. But let me think if we actually need some new weaponry to establish that. Okay, we'll come back to this in just a moment. I want to establish a unique, or not a unique, but a piece of weaponry which is going to be so powerful to help us establish this. So we will return to this. We'll return in a moment. We'll return to this in a moment. However, let's first roll back and look at one missing step in the proof which we actually did not solve the first time around. So all of this works under the assumption that there exists a path between RV and G, allows us to conclude that it lies inside HV. So here's the question. How do you know this is legit? Now certainly if the path is in the smaller guy, it must be in the bigger guy. But is it always the case that if you have a path in the bigger guy, you get a path in the smaller guy? Is that always true? So we're going to first prove this result before proceeding to one of the most powerful results in the idea of connected graphs. So let G be an undirected graph and V in VG be a vertex. For each n, we'll define a subgraph which looks very similar to our definition in the previous part. In fact, Gn is almost like HV. It's almost like HV, except now we ask for a path with this particular length. So now, here's the question. We're going to prove that for every n and x, you can find a path in between v and x. So it looks a bit like this. Here's x, well, here's v, here's x. Suppose you have a path inside Gn, right? And maybe you might even have a longer path. The idea is that no matter how many, no matter which length you have, you can always find at least one path of some length. So here's the proof. We'll prove by induction on the natural numbers. And so we'll start with the base case where n equals to 0, because we treat 0 as a natural number in this course. So for the base case when n equals to 0, we are gonna ask the question, okay, if n equals to 0, then can we find a path? Okay, so what's the claim, right? The claim is this. Here's our claim. For each n, right? Okay, we have this proposition, right? This is going to be our sentence. So for this particular n, we'll have this sentence over here. So for n equals to 0, we need to ask, okay, fix x inside v of g0. Can we find a path between v and x? Well, strictly speaking, what's in g of 0? G of 0 is the collection of points, or at least the vertices in g of 0 is the collection of points such that you have a path with length 0. There's only one item there, right? You must have x equals to v. And then, can you find a path from v to itself? Yes, you can assume, you can consider the nothing path, right? Which tells us that the empty set is a path. In fact, we can write it this way. The set containing v and the collection of no edges, right? Right, the collection of no edges. There are no edges is a path from v to v with length that's equal to 0. If you start at v, can you end up at v? Yes, just do nothing. That is a path. The do nothing path is considered a path, surprisingly. So we're done with the base case. That's the base case. Now what about the induction hypothesis? We'll suppose it's true for k equals to 1, 2, all the way to n. Suppose Pn is true for n equals to 1, 2, all the way to k. I'm just including strong induction here because I want to include more weapons. So if I can use more weapons, why not? Right? It's the way to go. Then the claim is that pk plus 1 is true. How do we show that pk plus 1 is true? We need to fix x inside v of gk plus 1. And what does that tell us about gk plus 1? Right? In fact, okay, pardon me, it's length 0, so therefore the path over here. So give me a moment. I just realized there's one technicality I missed here, and that is the path must lie inside g of n. That's the whole point. If it just lies inside the big guy, there's nothing to prove. But the fact that we defined it this way matters. So firstly, back to the induction hypothesis. Suppose that it's true for everything that's smaller than k, and we claim that the k plus 1 situation is going to be true. We're going to fix x inside v of g sub k plus 1. What does that mean? Well, it means that you can find a path between v and x with length less than or equal to k plus 1. Length, whoops, less than or equal to k plus 1. And here, for simplicity, let's assume that x is not equals to v. If it's x equals to v, we just recover the original result. So let's just assume that x is not equals to v, because that's a little bit less straightforward. So we have a path from v to x in g. Now, well, between v and x in g. And that's a little bit troublesome, but here's sort of the idea that I have in mind. Here's v, here's x, and you have a path. It looks a bit like this. Suppose it has length k plus 1. Suppose the length is k plus 1. Then you can sort of go backtrack by one step, and then what remains here has length k. And then you can slap on the induction hypothesis and try to make some conclusion from there. And this is where we'll need some thought. We need to put in some thought over here. So we'll write P to be from V, right, all the way to U and then X, right? Basically, that's conveying this idea here, right? What this tells us is that V to U has length less than equals to K, and therefore, if it has less than equals to K, right, if you have a path less than equal to K, then you can find a path between V and X inside G sub K. There exists a path between V and U inside G sub K. Now, we do not know whether this is the same path as the previous, right? All we know is that there is a path. That's all we know. We just know that there is a path. We don't know what path this is, right? So we do know that because V to U has length less than equal to K, which tells us that U lies inside V of G of K, and therefore you can find a path in G of K that contains U. Okay, so it's a little bit more technical, right? If you can find a path in G, then you know that U lies inside this set. U will lie inside this set. And if U lies inside this set, then you can find a path in G sub K, right? Now, of course, G sub K will be a path inside G sub K plus 1, which lies, and this path, we'll call this Q, lies in G sub K plus 1, because G sub K plus 1 contains all of the paths that have a length at most K plus 1. Right, so Q has length at most K, so clearly it has to have at most K plus 1. Yes, in fact, you might want to check this. You might want to check this using the definitions that this works. I'm sure it works, but you might want to check with the definitions. Okay, I don't even know whether we use this result, but now what remains is this guy over here. We need to sort of bring it home over here. Like, how do we sort of bring home the result from U to X? Because essentially we're using an induction argument, and essentially what we needed to sort of highlight was the fact that if we can go from here to here inside G of K, then we can go from here to here inside G of K plus 1. So let's see how this might work. Let's see what G sub K plus 1 is. Oh, I found it. Okay, so what this means is that if Q lies inside G of K plus 1, that tells us that U, which is a part of the path from between V and U, has to lie inside G of K plus 1 as well. Right? U has to lie inside G of K plus 1. Well, more precisely, the vertices of G K plus 1. Because the path lies inside G K plus 1, so U must lie inside the vertex set of G of K plus 1. But we know that X lies inside the vertex set of G sub K plus 1. So these two things combined together will give us that the edge XU lies inside the edge set of G of K plus 1. However, what that tells us is that we have a path, right? We have a path from Q, well, we have a path from V to U inside K plus 1, and then we have the path XU inside G sub K plus 1. So this tells us that we can find, using the path extension lemma, between V and X in G sub K plus 1. Right, this is by our path extension. if you can go from V to U, if you can go from V to U in GK plus 1, and you can go from U to X in GK plus 1, then you can go from V to X in GK plus 1. That's basically what we mean by a path extension. And that's the proof, and therefore we're done. Because what does it mean? We wanted to find a path between V and X inside G of K plus 1. And we are good to go. And that's that. So therefore, this has to be true by induction. So it's a little bit of bookkeeping and a bit of like that kind of shortening idea. So you sort of take the original object, you shorten it, you shrink it, you slap on it the induction hypothesis, and then you conclude whatever else you want to conclude. And again, path extension lemma and all these things are really useful tools to help you do just that. These are really, really useful and really powerful math results which you can use to prove certain statements. Okay, so that is the sort of the technical point, if you would, for proving that we can that every vertex has a connected component containing it. Now we haven't checked uniqueness yet, and I do want to check uniqueness in just a moment, right? But before we do uniqueness, we need this really powerful result called which is what I call the eating up lemma. So let me explain what this eating up lemma is. So this is G. Now this one, I believe in the course that is currently ongoing, this will be spring 2023 of CS1231. You actually have to prove this lemma yourself, right? It's actually not in the lecture notes, but here's how you do it, and you can sort of include it as your part of your help sheets and whatnot. Okay, so here's the eating up lemma. It's this statement, but let me illustrate this idea with a picture. So here is here's the point U, and suppose it lies inside some connected component H. So H is not just any object, it's not just any whatever, it has to be a connected component. Right? So it's sort of like the largest connected set that contains U. Now here's the idea. If for any point V, you can find a path that goes to U, then roughly speaking, V is connected to everyone, right? But H is by definition a connected component. It has to be the largest. So in a sense, and like this is why you call it eating up lemma, H will extend and eat up the path. So here's the technical definition. So for suppose that you have H containing U, then no matter which V you choose, if you can find a path from U, from P from U, between UV and G, like this, then, right, give me a moment, let me just check something. I think the quantifier here should be outside, so let me be more precise. Yeah, I think this should be a bit more precise. I think I should rewrite this way. So this one. This way. Sorry, give me a moment. Suppose, right, for any path P between U and V and G. There we go. I think it's for any path. For any path. Right? Or rather more precisely. Yeah, so I'll rewrite this statement this way. Give me a moment. Let me just very quickly change this statement here. This is a little bit sussy, so here's the statement. Alright, so then for any path P between U, V, and G, you will definitely get P is a subgraph of H, and V will be inside VH. Okay, so pardon me, but this is the eating up lemma. So let me repeat the eating up lemma over here. Now, what that means is that, once again, suppose you have a connected component H that contains U. right? Suppose you have connected component H that contains U, looks a bit like this. Then for any vertex you want, and for any path that connects U and V in G, right? For any path that connects U and V in G, this graph gets eaten up by H. That's what I mean by P is a subgraph of H. And furthermore, V being eaten up has to lie inside H. So in some sense, H will sort of eat up everything else. Right? So here's what I call the eating up lemma. It's a really, really useful lemma. So here's a very quick proof as to why this is the case. Well, since H is a... Well, let's just first prove it properly. So fix any vertex V in G and any path between U and V in G. We're working with these hypotheses. We're going to show that P is a subgraph of H and V is a vertex of H. So here's the fun part. So we're going to define H prime to be all of the items in H union with the path, with all of the items in the path. And similarly, it will be the edges in H union with the path. You can call this the union trick if you want. And I will leave you to check that H prime is connected. I'll let you check that H prime is connected. Well, because all of the items in H is inside H prime, right? All of these items are essentially inside H prime. H is a subgraph of G. Well, not G, of H prime. In fact, H prime is a connected subgraph of G. You can check this. And H is a subgraph of H prime. In other words, you have H is a subgraph. It's smaller than H prime, but yet both of them are connected, and this is a connected component. There's only one condition, there's only one conclusion we can get here. Well, H is a connected component of G. Once you have these three conditions, you have a connected subgraph, you have H being a subgraph of H prime, and H being a connected component, these three allow you to make a really strong conclusion that H must equal to H prime. This must be the only situation. But once you have H being equal to H prime, you are going to get V of H equals to V of H prime. But V of H prime is V of H union V of P. That's our definition of H prime. We define the vertex set to be these guys. And what we are left with is that vertex set of P must lie inside the vertex set of H. But recall that V lies inside the path, right? Because P is the path between U and V, so it contains V. So therefore we have V inside the vertex set of H. However, we also have that the edge set of H prime and the edge set of H must be equal to each other, which tells us that the edge set of H is precisely the edge set of H union the edge set of H prime. This tells us that the path is a subgraph of E H. But maybe we can do this in a bit more clean manner, slightly cleaner way, because this basically tells that E of P is a subset of E of H. The edges in P lie inside the edges of H. And with these two facts, we can actually use these two to conclude that P is a subgraph of H. And this is precisely our second statement. So in other words, if you can create a path towards U, you can eat up the path. and everything in it. If you can connect it to an item inside the connected component. This is a really, really powerful lemma. With this lemma, we can now go back to one of our results that we wanted to show just now, which is the uniqueness property. We come back to this uniqueness property, right? Because now we can claim, okay, so claim, let H and H prime be connected components of G containing V. We claim that H must equal to H prime. So what's the proof? The proof is this, right? So we can use the eating up lemma. We're gonna try to use the eating up lemma. So how do we show this? Well, we can show that we can show it suffices to show that you get a subgraph. Okay, so now I'll leave you guys to check that once you get that H is a subgraph, you can get equality. Okay, so to do that, we will need to show that the vertices of H is a subset of the vertices of H prime, and the edges of H is a subset of the edges of H prime. And to do that, what is our objective? Well, V of H is a subset of V of H prime, so we need to fix any item U inside V of H. Right? So what does that tell us? By definition, right? By definition, because U is in the connected component of V, well, a connected component containing V, there exists a path from U to V, between U and V, in H, right? Right, there is a path between U and V in H. So here's the picture. Let's just draw a picture over here. Okay, so suppose here's H prime, and here's the point V and U, right? So sort of we want to create a path this way. In fact, the path is not in H, the path is in G, to be more precise. Is it in H or G? I think it is, well, I think we can just use G. Oh, we can use H, I think we can use H. Right, we can use H. So it looks a bit like this. Right? And now, here's the fun part. Right? Okay, so in fact, we can actually prove both in one shot if I'm right. So here's the fun part. So we'll fix U and V in H. Well, we'll fix U in V of H. Looks a bit like this. And then there's a path between U and V in H, right? But since V is in H prime, and H prime is a connected component of G, right? By the eating up lemma, we can say that P is a subgraph of H prime. And if P is a subgraph of H prime, this tells us that U must lie inside V of H prime. So that's a pretty fun result there. Now what about the edges, right? We've done it for the vertices, so we can conclude. The conclusion here is that V of H is a subset of V of H prime. But what about the edges? Well, fix UV, UW inside V of H. Well, not V of H, E of H. Right? Fix U and W inside the edges. This tells us that U and W both lie inside the vertices. And therefore, there exists a path between U and V, right? There exists a path between U and V, and you can assume it. There exists a path between U and V, in H, and therefore you can check that the path, right, from W to U all the way to V lies in H. So once again, now we have a situation that looks a bit like this. Here's the edge, and now this entire path lies inside H. And it lies inside H and it connects to V. Once again, right, since V lies inside H prime, which is a connected component of G, by the eating up lemma again, we can say that the path WU is a subgraph of H prime, but that means that the edge UW must lie inside H prime, and this helps us show that E of H is a subset of E of H prime. And that is how we can use the eating up lemma to establish certain results. Roughly speaking, if you can connect into a connected component, then the connected component must eat you up. It's sort of like that. That's why I named it the eating up lemma, for that reason. I like this result a lot. It's a very, very cute and clever result. So yeah, that's the eating up lemma. And there's that. Now we can check a few more results on connected components. So let's do just that. Okay, so we'll let G be an undirected graph and H be a connected component. Then the edges of H must be equal to this particular set. And let's just work it out. So proof. So we'll first go in this direction. Right. So we'll fix X and Y inside the, well, apologies. We'll fix XY in E of H. Of course, you could end up with loops, but I'm just gonna assume it's not loops for now. The argument's the same, so it's not a big problem. Then, if XY lies inside EH, then X must lie inside V of H, and Y lies inside of V of H as well, right? Because if there's an edge in H, then the 2 points will lie inside the vertex set. Right, and then on the other hand, the edges of H, because H is a connected component, it is a subgraph of G. Right, so therefore, XY will lie inside the collection of edges such that each of the constituents lie inside the vertex set. I think this is fine. Finally, let's go the other direction. We'll fix X, Y inside this guy. Right? So this tells us that X and Y lie inside the vertex set that contains H, and our goal is to check that XY is an edge. Our goal is to show that XY lies inside E of H. I think that's not too bad. And the reason why, once again, is the eating up lemma. I can't believe we're just spamming this eating up lemma again and again. So here's X, here's H. Now Y is actually inside as well. But let's just put Y outside just for the sake of visualizing it more clearly, because we don't know whether the edge lies inside. So X, Y is in EH. So since XY is a path between Y and X, but X lies inside the vertex set of a connected component. Once again, by the eating up lemma, we must have that the path XY is a subgraph of h, which tells us that xy as an edge must lie inside the edge set of h. So yes, the eating up lemma is very, very useful lemma to sort of use in various kinds of proofs. It's amazing. Alright, okay, we are left with a few more questions, but perhaps it might be useful to go for a short break. But we will be back. We'll be back in 5 minutes, and we will come back to see how we can solve the remaining problems. And we may or may not use the eating up lemma again, but we've already used this 3 times. So it is a really useful lemma to bear in mind. Alright, we'll go for a short break because I need a breather. It's 2 hours of math and I need a break. We'll be back. Alright, let's go ahead and resume the stream. So we've looked at a bunch of ideas in graph theory so far. Maybe a quick recap of the big ideas that we discussed. So firstly, we looked at the notion, the definition of graphs. We've tried to count the number of complete graphs. We tried to introduce the idea of using induction as a proof technique for many of these graph-related questions. We've applied some counting ideas here. We've talked about cycles, loops, paths, all these kind of things. We've looked at the path extension lemma, which basically says that if you can go from point A to point B and then point B to point C, you can go from point A to point C. It's that straightforward. It's an extension of the path. And we have the two-path lemma. So in other words, you get two paths precisely when the thing is a cycle. You get the idea of connectedness, isomorphic graphs, all that good stuff. You get to draw isomorphic graphs. And we talk about connected components. Right? Connected components, a really important idea because it talks about basically the largest connected set that contains whatever you want it to contain. I think we can generalize this to higher, like infinite sets and whatnot. So if you're interested in infinite graph theory, that's on you. And we have, of course, my favorite result here called the eating up lemma, which basically allows you to let the connected component eat up any path that enters it. It's that simple. Right? So now let's look at this question on undirected graphs, which are with exactly n vertices and no loops. So if we have this situation, if the number of edges is bigger than this guy, then G is connected. Now it's really hard to argue about number of edges. Any statement involving number of edges, it's generally a very difficult argument. In the next stream, when we look at trees, we can sort of argue it, but even then it's still not very straightforward. So how about, let's suppose, right, let's prove the contrapositive, which tells us that if G is unconnected, or rather, if G is not connected, then the number of edges in G must be upper bounded by n minus 1 over 2. N minus 1 choose 2. And here's how we're going to go about it. Now, if G is not connected, since G is not connected, you will be able to find 2 points such that there is no path between them. So what that means is it looks a bit like this. You have V, you have U, and they belong to their own islands. Right? They belong to their own islands. You can't really go from one island to the next. So here's the idea. Looks a bit like this. For example, right? It looks a bit like this. So in a sense, you cannot really, it's almost like these edges are out of bounds. That's the idea, right? The idea is sort of you can't really connect anything over here. Right? So we want to sort of convey this idea. So here's how we'll do it. We will define HV to be the connected component containing V, right? More precisely, connected component of G that contains V. And we'll define H prime not as the component that contains U. I mean, that's fine. But why not let's just define H prime to be everything else? Let's just define H prime to be everything else. And then what we do have, right, is that the number of edges in G will be the number of edges in HV plus the number of edges in H prime. So that's the idea, right? If we just define H prime by definition to be everything else, then we can get the edges of G by adding up the edges of the individual items. Okay, but how do we go about this? Well, here's the little sneaky bit that we have here, right? The idea is that this graph here, and we are working in the situation when, this graph here, it looks like this, and we're working in a situation when there are no loops. We're working in a situation when there are no loops. So if we're working in a situation where there are no loops, in a sense, it has to be smaller than the maximal graph in this region. I can't draw it completely because, you know, I can't do art. But if you were to connect all the different possible items there, you're going to get that H prime must be a subgraph of the complete graph on this number of vertices. It has to be a subgraph of that complete graph isomorphically, right? And likewise, HV is a subgraph of K of the complete graph on, well, say, the number of vertices here. In some sense, because it's like the biggest element. It's sort of like the biggest graph that contains all of the different possible vertices. Biggest loopless graph in that sense. So, why is that useful for us? It's because we can now say that we can upper bound this aspect by, we can upper bound each of these quantities by the number of edges in the complete graph. Right? Number of edges in the complete graph. We can upper bound it this way. And if we can upper bound it this way, then something amazing happens. Right? Something amazing happens. We know how many edges there are in a complete graph with this number of vertices. It's going to be that number over 2. Well, I think it's apologies, let me try that again. It's a bit awkward. Is this number times this number minus 1 over 2. E of HV over here is upper bounded by this expression, and E of H prime will also be upper bounded by this expression. So we can combine the upper bounds and we will be good to go. So let's finish this up. E of H prime will be upper bounded by E of the complete graph on the vertices of H prime, which is the vertices of H prime, vertices of H prime minus 1 over 2. This is the number of edges in a complete graph. Now, things are a bit complicated with all these letters floating around. Let's just give it some new names. Let's call this K. And let's call this L. Okay, so let's put some notation here. Firstly, V of HV is equal to K. Next, V of H prime is L. And finally, these two must add up to N, because we're working with a total of N vertices. Right? We will give N vertices. And all that remains is some algebra. We just need to algebra and we're good to go. So once again, let me repeat that what we're trying to do is upper bound this quantity. We're trying to upper bound it by, hopefully, we want to upper bound it by n minus 1 over n minus 1 choose 2. Hopefully, we can upper bound it that way. So let's upper bound it. Let's upper bound this by k minus 1 over 2, l minus 1 over 2, and we are going to do a little bit of algebra. And I think I want to do the algebra here because it doesn't come across to me as really obvious how we should go about it. So this will be k squared minus k plus l squared minus l. And this will simplify to k plus l squared minus 2kl minus k plus l. I believe that is how it works. We will need to do a bit of algebra. Okay, maybe I might avoid doing this. Let's just expand out everything and see what we get. I'm going to expand out the L because k plus L equals to n. This comes from this equation over here, which tells us that L equals to n minus k. Hopefully things will cancel out. I think it will. I think it will. But let's just do it properly. So this is gonna be n minus k squared minus n minus k. The linear terms, the non-quadratic terms, will simplify very nicely. But let's just do algebra. This would be that. And then we can write this as half of n squared minus n plus 2k squared minus 2nk. Part of me thinks there's something a little bit sus about this working over here. There's something not quite adding up as much as I want it to. I mean, we could try to make a case that well, this is awkward and embarrassing. Okay, I think I found it. I think I found the final piece of the puzzle. Right, so this requires a bit of effort, a bit of techniques in upper bounding. So let's upper bound what we can. I believe we can write this as 2k of n minus k. There we go. We can write it this way. I believe we can write it this way. There's a bit of algebra there. And the reason why we write it this way is because this term, k, what was k again? K was the number of vertices in HV, which means that n minus k, so in other words, k has to be smaller than or equals to the total number of vertices, which means that n has to be n minus k has to be non-negative, and k is the number of vertices, so that's non-negative as well. So all of this is to say that the n minus k is non-negative, the k is non-negative, so the entire term, including the negative sign now, is going to be negative. Which means this is going to be upper bounded by half n minus 1, because that's the factorization for n squared minus n. And finally, this equals to n minus 1 choose 2. And that's that. So here's the general proof. Here's the proof of the entire result. If we claim that if it's not connected, then we must upper bound it by n minus 1 choose 2. We'll split it up into a connected component containing v and everything else, which we don't really care. We just don't care. We contain them within the complete graph. And then we bound it above using the number of edges or vertices in a number of edges in a complete graph. And then we algebra our way to victory. So that's the big picture proof of this claim. It's a rather interesting claim, I have to say, but it is what it is. So feels good. Alright, so here's a related question. Suppose instead now we have a graph with this many edges, or bounded above by this many edges. By the way, this simplifies to 3 choose 2, which is 3 times 3 minus 1 over 2, which is just 3. So how many graphs are there such that you have 4 vertices and no loops? Well, I think we checked this the other time, right? I think we actually solved this the other time. So 4 vertices and no loops. So let's just check how many graphs do we have. That has at most 3 edges. I think I can see where this is coming from. We actually solved this just now, right? So once again, here's the no edge situation, the 1 edge situation. You have 2 graphs with the 2 edge situation, and then you have 3 graphs with, oh gosh, no. 3 graphs with the 3 edge situation. 1, 2, and 3. Alright, so the total is going to be 1, 2, 3, 4. Well, did I mess this up? Yeah, I messed this up, darn it. 1, 2, 3, 4, 5, 6, 7. We should have a total of 7 graphs. Because with 7 graphs, yeah, we should have 7 graphs. Right. Unless we have... Okay. I think I read the question wrongly, but let me just take a look at what was the question for this bit over here. Oh, I missed one keyword over here. Connected. How many connected graphs do we have? Well, now if it's connected, all of this just goes out of the window. These two as well. So, nope. No. Right, we're left with these two graphs. So the total here is 2. Right, the total number here is 2. We have a total of 2 graphs which are connected. Okay. We have a few more questions to go, and these are the longer proof type of questions. I do want to go through them. I want to show the power of the eating up lemma as well. So here's the claim. Suppose we have a bunch of connected components, then we can form a partition. So the idea is, roughly speaking, if your graph looks a bit like this, let's say this way, well, then we want to claim that these connected components, in a sense, forms a partition of the entire graph. Almost like constellations, now I think about it, but you know, you get my point. So that's the idea. And well, how are we gonna prove this claim? Darn it. Here's how we're gonna prove it. I'm probably gonna need more space, but we'll create more space when we need more space. That was just circular explanation right there. So here's our proof. We're gonna define basically these guys. V of h is the vertices in one connected component. So this set of vertices and this set of vertices and this set of vertices, we claim this forms a partition of, well, all of the vertices, which does make sense. But what do we mean by a partition again? So let's just recall what a partition means. For it to be a partition, we require 3 criteria. So firstly, for any h, which is a connected component of G, we need to show that V of h is non-empty, and likewise with E of h as well. So we are gonna prove both V and H and V of h and E of h in this run through. I know for some there were some other attempts where we split them up, but in this attempt we're actually gonna put them together because I think it's possible. So that's the idea. Now, secondly, what we need is that the unions of the VHs across all the connected components, if you take the union of all the vertices, you get the vertex of everything. And then, if you take the union across all of the edges, you're going to get the edges of everything. So that's the second claim. Now the third claim is the claim that if you have two connected components, or rather we'll put it this way. If you have a bunch of vertices, right, like this, right, and if they don't intersect, then they must be equal to each other. So in other words, for example, if you have this guy and some other connected component that does not intersect, it has to be the same connected component. There's no other option. You can see where we might be going with this, with the eating up lemma. And then similarly, if the edges don't intersect, then they must be the same set of edges. And you can probably imagine that number 3 is where we'll use the eating up lemma. Now, let's go ahead to prove each one of them. So, let's take a look. Now, firstly, by our definition of E of G, this is not possible. It's definitely not possible, right? By our definition of E of G. But, what about V of H? Okay, so let's create some space here. In fact, we'll probably need to do this in a new page. So let me just set this up properly. I realized I didn't set this up as properly as I hoped. We'll probably need 3 different pages. Most likely. It is a rather long proof. There we go. Okay, so let's go ahead to prove these results. Okay, so first one, we need to show, I think this is pretty obvious by the definition, you can check it if you wish, but this one is not as straightforward. And here is the idea. Okay, so, well, suppose for contradiction, that V of H must be empty. Then E of H actually this is actually not as obvious as it seems, right? This is actually not as obvious. We actually need to check that this is non-empty as well. Okay, so then if E of H, okay, if the connected component has no vertices, then it can't have any edges, right? There's nothing to connect. So in other words, we're gonna get equals to empty set, which tells us that H will be an empty connected component. Now it still is a connected component, it's just empty. Now, we know that we know that G has at least one vertex, and what it tells us is that there exists some V inside the vertex set of G. Right? We know that we can find at least one vertex. We don't know which one it is, but we do know there is one. But if you have a vertex, then you can find uniquely a connected component that contains V. You can show, well, we've shown just now that the connected component must be unique. HV of G contains V. And so, what does that mean for us? Right? So we call that over here that that H here is a connected component of G. Then what we have here is that H, firstly, H is a connected component of G. Secondly, because the empty set is a subset of the vertex set of HV, and the empty set is a subset of the edge set of HV, right? Because these two things are true, we must have that H H is a subgraph of HV, right? Because this guy, right, the vertex set of H is smaller than the vertex set of HV, and the edge set of H is smaller than the edge set of HV. So H must be a subgraph of HV. But if H is also a subgraph of HV, and we know that HV is connected, and we know that H is a connected component, what can we derive? We can derive that HV equals to H. But that means that VHV equals to V of H. Which means that VHV is empty. But V lies inside VHV, which means that VHV is non-empty. So we have a contradiction. We have a contradiction because V of HV cannot be empty and non-empty at the same time. And therefore, we contradict that VH is empty. Right? Conclusion, VH is non-empty. Okay, now for the edge situation here, we have to be a little bit more precise. It's more not any H in CC of G, but it is for any H in E of G. By definition, or rather for any E of H in G. For any E of H in E of G, then by definition, the edge set of H cannot be an empty set because we're excluding the empty set from the possibilities. So that's just a slight technicality, but most of the heavy duty still comes from showing that the vertex set of a connected component cannot be empty. Well, if the graph is, if G is a, is a non-empty graph, then you can't have that, which is pretty crazy. And therefore, what does that tell us? Okay, therefore, we get this property, and we are one step complete from proving our result. Finally, secondly, let's go ahead to prove that we have that the unions will give us everything. So I'll let you guys very quickly check that this direction is obvious. This is pretty obvious. I'll let you guys check it on your own. But to check the other two sides might take a bit of effort. Not too much effort, but just a bit. So let's go. So for the first part over here, let's establish this result. We'll fix any vertex in the vertex set. But if you have a vertex in the vertex set, you can find a connected component that contains it. In fact, this connected component is going to be unique. It's going to be unique. But that means that V lies inside the vertex set of that connected component, because V is a vertex inside that connected component, which lies inside the union. And it still works. Now, what about this bit over here? What about the edges? We'll fix UV inside the edge set of G. I think some of you can see where we're going with this. What that tells us is that, well, U and V are vertices in G. But we can find a unique connected component, HU, of G that contains U. And once again, here's U. Here's the connected component containing U. And here's the path UV. In fact, the path is just direct. So once again, by the eating up lemma, we've been abusing this lemma like crazily much. The path UV is a subgraph of HU. But if UV is a subgraph of HU, that tells us that UV lies inside the edge set of HU. But if it lies inside the edge set of HU, it lies inside the unions of the different possible edge sets. And we're done. So the eating up lemma is pretty... I like this a lot, I have to say. It's a really, really nice result. It helps you prove a lot of things. It helps you sort of show that things that are outside of the connected component actually lie inside the connected component. And that is really, really useful. It helps us prove many, many things. So please abuse or use that for your advantage. Okay. We have one more result to go. And once again, we'll need the eating up lemma yet again. I'm just going to keep using this eating up lemma, so you might want to include it in your help sheets. Okay. Finally, we need to show this property that if VH prime and VH, if VH and VH prime are non-empty, then VH equals to VH prime, and likewise with the edge set. So here's how we're going to prove it. So we're going to prove the vertex situation first. So we'll fix V inside this guy, or rather, since it's non-empty, there exists a V such that it lies inside both connected components. And how do we show that this is true? How do we show this is true? Again, I'm gonna show you, or rather, I'm just gonna claim that you get a one-way subset. And I'll let you check as an exercise that this will imply this result. You can check this as an exercise. Okay, I'm just gonna show one subset. In fact, we've actually proven something very similar to this just now, but it's all good. In fact, it might be the same result. So, in fact, I don't even think we need to prove that much, right? Because check this out. Okay, we've actually proven earlier on, right? We don't even need to do this, Lemma. Okay, nice. So, firstly, you know that H and H prime are connected components of G containing V. This is by definition. At the same time, you know that since V lies inside V of G, there exists a unique connected component, HV, such that that contains V. So on the one hand, you have two connected components that contain V. On the other hand, you know that the connected component containing V must be unique. We proved this earlier on just now in one of our results, and this tells us that H must equal to H prime. Now here's the beautiful thing. The beautiful thing is that if H equals to H prime, then the vertex set of H must equal to the vertex set of H prime, and the edge set of H must equal the edge set of H prime. The reason why is because we actually proved this earlier on using the eating up lemma. Right? We actually proved this earlier on, showing the uniqueness of the connected component, and that's pretty cool. That's pretty cool. And so we have that result as well. Of course, we are assuming that EHs here are non-empty. Yeah, the argument will work. The argument is going to be exactly the same for the edge case. Okay, so that's it. That's how we can show that the VGs form a partition and the EGs form a partition. We take advantage of the fact that the connected component containing the single point must be unique. It's the only one. So we can use this to derive the partition properties. So I have to say that's a very clean proof. I like that a lot. I genuinely like that a lot. We're almost done. We're gonna look at one last idea called the complement graph, and then we're gonna call it a day. So here's the question: draw the complement of the following graph. So we say that the complement of this graph is going to be given this way, okay? And of course, it's going to be a graph with no loops, correct? So it's going to look a bit like this. So we'll ask the question, well, is 1 and 2 connected in the original graph? It's not, so we're gonna connect them. And is 1 and 3 gonna be, are they connected in the original graph? Well, they are not connected in the original, well, they are connected in the original graph, so they won't be connected here. What about 1 and 4? Well, sorry, what about 1 and 4? 1 and 4 are connected in the original, so it won't be connected here. What about 1 and 5? Well, 1 and 5 are connected here, and they won't be connected here. So, well, they are not connected here, and therefore they will be connected here. And likewise for 6. And you can check this with 2 to 3, 2 to 5, 2 to 6, 3 to 5, 3 to 6, 4 to 5, 4 to 6. I believe this is our complement graph. This is our complement graph. So that's a bit of a warm-up, and I actually want to keep this picture here for the next part because we're going to try to make an interesting observation over here. If we notice very carefully, the graph on the left is connected, and the graph, well, it's not connected. This graph is not connected, and this graph is connected. And so that raises the question of, well, if this is not connected and this is connected, can we have two graphs that are not connected? Turns out that you must have at least one of them which is connected. And right now, I'm trying to think if there is a shortcut to prove this, because I feel like I've proved a result earlier on that helps me check for some information. Okay, so no, I don't think we'll get anything useful. Okay, it's all good. Okay, so let's try to prove this result that if you have one guy, or rather you must have at least one of these guys to be connected. You cannot have a situation where there are two things which are unconnected at the same time. You cannot have a graph and its complement both unconnected. So let's go ahead to establish this result, and this is the last result for the day, and we're gonna call it a day, and we'll look at trees tomorrow, which is the last stream for discrete math. So here's the proof. How do we start? How do we start? Well, I'm trying to prove this by contradiction. That's the idea. And well, okay, let's go this way. So we have two cases, right? Either G is connected or G is not connected. Right? If either G being connected or not. Now if G is connected, then the disjunction is true. We're done. We're done. If G is connected, we're done. So now let's suppose that G is not connected. This tells us that it has at least two connected components, right? So let's just argue it properly once again. So there exists U and V in the vertex set such that there is no path between U and V in G. We'll define HV to be once again the connected component containing V. And H prime, we're going to define it to be once again everything else. This isn't a complement graph, by the way, so it's not the complement graph, just to highlight, just to emphasize the point. Right, but it is sort of like saying, okay, here is H of V and here is H prime, right? So that's the idea there. So what do we have if we have HV and H prime? If we have HV and we have H prime, then the idea is that, okay, so here's H prime, right? Roughly speaking, this is H prime, and this is HV. right? The idea is that anything in H prime, okay, anything in H prime cannot be inside HV. Right? So that's the idea. Okay, so we have the idea here. Now, we do know that the vertices of the complement graph will be these vertices. This is V of H complement, but it turns out that, well, V of these vertices will be the same vertices as these guys, right? So this still is V of H prime, although the edges are completely different. The edges are completely different, right? So in other words, we can fix U, well, R and S inside the vertex set of the complement graph. Now the first situation is that, well, let's break it up into a bunch of cases. Case 1, R and S lies inside the vertex set of HV. Well, this is not very convenient, right? In fact, let's do it this way first. Let's suppose R lies inside the let's do it this way. Let's suppose R and S lie inside the vertex set of H prime. And this will give us two different possibilities. We know HV is connected, that's not a question. But H prime, we don't actually know whether it's connected or not. And that's not a problem, right? So here's the idea. Suppose, right, R and S are not connected, right? Or rather, yeah, R and S are not. Okay, let's just do it this way. Suppose there is no path from R to S between R and S in H prime. Not in H prime, in G complement. Sorry, what am I saying? In G. So in other words, for example, you have, let's just say we're looking at a slightly different situation here. Let's suppose we have this hypothetical situation. This is our HV and this is our H prime. So in other words, suppose you have R and S and there's no path between them. Well, then it's really straightforward. Then there will be a path, right? Okay, so maybe we can do it this way. So suppose RS is not in the edge set. Well, then just connect them in the complement. That's the definition of a complement and we're good to go. And therefore, there is a path between R and S inside G prime. In G complement. Inside of G complement. Okay? So, if they're not connected originally, then just connect them in the complement. That's not hard. Now, what if R and S are connected inside the original graph? For example, what if R and S are connected? Well, then we do know that even though R and S are connected here, they are not connected to HV because there's no path to HV, right? So note that there is no path between R and V in G. And there's also no path between S and V in G. So I'm gonna let you guys do a bit of bookkeeping over here to do a bit of checking that if you have no path inside the original, you must have a path in the complement. There exists a path between RV in G complement, and there exists a path between V and S inside G complement. So this allows us to deduce that by the we can piece together, right, by the extension lemma, path extension lemma, because we can go from R to V and then V to S, which means we can go from R to S. So therefore, once again, by a path extension, we can go to from R to S inside G complement. That's the first instance in which R and S both lie inside H prime. And we're actually not too far off from the rest of the cases because we've sort of established all of the different possibilities. But let's take a look here. Secondly, R and S lies inside V of H. Right? The R and S must lie inside V of H. Right? In fact, okay, you can do this, but maybe we can actually simplify this. We can simplify this argument here. Right? We can simplify this argument here. Let's make it a bit easier. So we know that over here there is no path from R to V, which tells us that RV is not inside E of G, and VS is not inside E of G. This tells us that, okay, we can get these guys. This tells us that RV lies inside the complement, and VS lies inside the complement as well. And finally, by the same argument, by path extension, we get this result. Right? By path extension, we can go from R to S. Right? Now for RS in VH, I think we could make the same argument. Right? If R and S are in VH, you can actually make the same argument as before. So I'm going to let you try this as an exercise to show that you can always still find a path between R and S inside G complement. Still doable, can be done, and I think the argument is going to be basically the same argument. But the third case is the easiest because if R lies inside V of H and S lies inside V of, well, this is HV, apologies, and S lies inside H prime, this tells us that RS is not inside E of G because they are in different parts, which tells us that RS lies inside the complement. And finally, this by definition means that we can get this result once again. So by splitting into the different cases and by partitioning it properly, we can get a really short proof for an otherwise long and complicated question. And I believe that's it. I believe that's all for graph theory for now, and we'll come back to do trees and wrap up discrete math tomorrow. So I'll catch you guys in the next one.